Hey everyone! Welcome back to today's lesson on attenuation in ultrasound imaging. This lesson focuses on incidence, particularly how incidence angles predict ultrasound energy behavior. Understanding the behavior of ultrasound waves at tissue interfaces is fundamental to diagnostic medical sonography. Let's get started. Once an ultrasound wave leaves the transducer, it begins propagating through the body. Eventually, this sound wave will strike a boundary, whether that be between muscle and fat, soft tissue and bone, or any other two mediums. The pulse may reflect back towards the transducer or continue transmitting past the boundary, dependent upon the acoustic impedance differences and the angle at which the ultrasound beam strikes the interface. We discuss acoustic impedance differences in depth in other lessons. When an ultrasound beam strikes an interface at 90 degrees, we refer to it as normal incidence. Another way of thinking about this is if the ultrasound beam hits a boundary between two mediums, like soft tissue and bone, perpendicular to the boundary, then it is considered normal incidence. If the ultrasound beam strikes the interface at any angle other than 90 degrees, we call it oblique incidence. The angle of incidence impacts how the reflected and transmitted parts of the beam will behave. Imagine you're standing on a tennis court and you drop a tennis ball straight down onto the ground. The ball hits the ground at a 90-degree angle, bounces straight back up, and comes right back to your hand. This is like normal incidence in ultrasound, where the sound wave strikes the surface of a structure at a 90-degree angle, perpendicular. At normal incidence, most of the energy is reflected back in the same direction it came from, making it easier for the ultrasound transducer to detect the returning signal. Now picture yourself tossing the tennis ball toward the ground at an angle instead of dropping it straight down. The ball strikes the ground at a slanted angle and bounces off in a different direction. This is like oblique incidence in ultrasound, where the sound wave strikes the surface of a structure at an angle other than 90 degrees. With oblique incidence, the reflected wave travels off in another direction, making it harder for the transducer to receive the signal. Additionally, part of the energy might be refracted or bent into the tissue, further complicating the process. In normal incidence, when the beam strikes the boundary between two mediums at 90 degrees, the reflected and transmitted waves will travel along the same path as the incident wave. This means the reflected energy will travel back along its original path, while the transmitted energy will continue forward on its original path. With normal incidence, reflection will only occur if there are differences in the acoustic impedances of the two mediums. Remember, a small difference in acoustic impedance between two mediums results in a small amount of reflection. A large difference in acoustic impedance between two mediums results in a large amount of reflection. No reflection occurs if there is no difference in the acoustic impedances between the two mediums. Acoustic impedance and angle of incidence also impact transmission. A small difference in acoustic impedance results in a large amount of transmission. A large difference in acoustic impedance results in a small amount of transmission. All of the energy is transmitted if there is no difference in the acoustic impedances between two mediums. This discussion becomes more complicated when looking at oblique incidence. Again, this is where the sound beam strikes the boundary between two mediums at any angle other than 90 degrees. With oblique incidence, we cannot predict whether sound will reflect or transmit after striking the boundary. Reflection may even occur when the acoustic impedances of the two mediums are identical if the sound wave strikes the boundary obliquely due to conditions like the momentum of the sound wave or the homogeneity of the boundary. Homogeneity of the boundary refers to any irregularities in the boundary's surface. Reflection may not even occur when the acoustic impedances of the two mediums are different if the sound wave strikes the boundary obliquely. It's kind of like dropping a tennis ball. You have no idea where the energy might take the ball next. When looking at reflection in oblique incidence, we have to take into account conservation of energy and the incidence angle. With conservation of energy, we know that there is no energy loss at the boundary. So, the percentage of reflection that occurs at the boundary plus the percentage of transmission that occurs at the boundary must still equal 100%, just like in normal incidence. We can also look at the angle of incidence to help us better understand reflection behavior in oblique incidence. In normal incidence, the incident angle is 90 degrees, so the reflection angle is 90 degrees, straight back towards the transducer. In oblique incidence, the incident angle may be 45 degrees. In this case, the reflection angle will also be 45 degrees. The reflection angle is always equal to the incident angle. This means that the signals reflected back from the boundary will be weaker than in cases of normal incidence. This can result in weak or missing echoes, impacting image quality. Oblique incidence also impacts transmission. Again, the behavior of the beam becomes unpredictable during oblique incidence. The part of the beam that is transmitted may continue traveling straight ahead, or the beam might bend or change direction entirely. When the beam bends, we call it refraction, which can distort the image if we are not accounting for it. We will discuss refraction and the impact of oblique incidence on transmission in more detail in a different lesson. In summary, both acoustic impedance differences and angle of incidence impact the behavior of the ultrasound wave at interfaces between different mediums. In normal incidence, the beam strikes the boundary at 90 degrees, and any reflection that occurs travels back along the beam's original path, while any transmission that occurs continues traveling along the same path. In oblique incidence, the beam strikes the boundary at any angle other than 90 degrees. Reflection and transmission become difficult to predict during oblique incidence.